Okay. Hello, everyone. Good morning from Honolulu, and thank you for being here. Today, I'm going to be talking about some new work on global diversification dynamics in turtles that has really arisen out of this now multi-year effort to assemble a large phylogeny for all turtles that Phil Spinks, Brad Schaefer, and I have been working on. Now, before I get into the details, I want to start by saying thank you. Thank you to TSA specifically. Assembling the necessary samples for this tree has really depended on this group of people. It truly wouldn't have been possible without your help and many others, so we appreciate it. So this is what the tree looks like. It samples 80% of the extant species of turtles. We got all the genera in it represented, except for 2, and then all of the families. The data here are coming from 15 nuclear loci. And we're at the point now where the tree is sort of in hand. We have this nice statistical estimate of evolutionary history, including timing. And now we're at the point where we're starting to use this tree to address some evolutionary questions. The one I'd like to talk to you about today is a really simple one, and that is, why are there so few turtle species? Why are turtles so undiverse? So we all know that turtles are an ancient clade. They're much older than many other of the major lineages of vertebrates, and yet they contain a tiny fraction of the species diversity. So if we take the number of species in each clade and just divide by the age of that group, we get some sort of species per million years. And based on this, it sure looks like something different is going on with turtles. And we were interested in trying to dig into this and maybe understand what's happening. So we can dig into the literature, and most of the relevant work here really comes from the fossil record rather than from molecular work. So I'm showing you now some classic work from the early 90s from Hutchison. This is based on fossil turtle communities in the Western United States. And what I'm showing you here is simply a list of genera that are known from this formation. The black bars are time periods when fossils have been found. And we see, as time runs along, right around 34 million years here, we seem to have this extinction event in the fossil record where many species or genera disappear all at the same time. Now, the interpretation from this work is that this is really arising from the cooling and drying process that was happening globally at this time. So the transition from the Eocene to the Oligocene is known as a period of cooling and drying, and specifically in Western North America as well. Other work from the fossil record has taken different tacks looking at these associations between environment and turtle diversity. Here's an effort to model paleoclimate envelopes of fossil turtles. And what we find here is an association between warm mesic habitats and more turtle diversity. Okay, so on the one hand, we have cool and dry and decreases in diversity. On the other hand, we have warm and wet and more diversity. We start thinking maybe there's a role of climate in regulating the diversity of turtles. And we wanted to try to investigate that further using the new phylogenetic tree that we have assembled. Okay, so to explain how we do this, we really just need to start from a simple hypothesis. So let's imagine for a moment that regional extinction event in Western North America, rather than being regional, is actually global. So if that were true, we might expect to see a slowdown in diversification rate at the point in this tree that corresponds to the Eocene-Oligocene transition. Okay. So the model here is relatively simple. Essentially, we draw a line down the middle of the tree. We estimate rates to the left of that line and estimate rates to the right of that line. If diversification rates go down to the right of the line, we may view that as being concordant with this idea of an extinction event at the end of the Eocene. Now, that's a very specific hypothesis. We don't want to restrict our attention to that. For instance, maybe there is a global slowdown in the diversification rate, but we got the time wrong. Maybe it's a little earlier, right? So we want to be able to account for that hypothesis, or maybe there's more than one break in the tree, and only one of those is the one that we're sort of focused on right now. And in fact, if you think about it, there turns out to be an infinite number of these sorts of models that incorporate different numbers of shifts in the diversification rate as well as their timing. Okay? So in the face of this model uncertainty, rather than focus on any one model, what we do is use Bayesian methods to integrate across all of them together and then average those results in proportion to their fit to the data. This is what those results look like. So I've dropped a red line into this tree that corresponds to the Eocene-Oligocene transition. And the chart in the bottom here sort of shows our average diversification rate through the history of this tree. And we have a long period of relatively constant rates, punctuated by one roughly threefold speed up that starts in the Eocene and seems to happen right around that transition. So that was sort of a head scratcher for us. We saw that and like, well, it's kind of the opposite of that pattern from Hutchison. So what's going on here? So to dig into this, I want to just sort of walk you through a few facts. So this is a map of global diversity in turtles. Warm colors are more diverse. And the first thing I want to point out is these studies from the fossil record, as we all know, come from a highly incomplete source of data. The fossil record is highly incomplete and biased. So specifically, this Hutchison paper comes from an area in Western North America that essentially doesn't support turtles today at all. The paleoclimate paper uses more global sampling of fossils, but again, we're very restricted in our attention to specific areas. So it's certainly possible that something different is going on with the extant diversity that's represented in our tree. The second thing I want to point out is this period of global cooling and drying towards the end of the Eocene was sort of a major event in the history of the Earth, in that it changed many other things, including sea levels. So here I'm showing you the changes in temperature across time as well as sea level. And you can see there's major decreases in sea levels, like on the more than 100 meters. So this is a much larger decrease than we tend to think about today with climate change. And these magnitude of sea level changes really have an impact. They reshape coastlines and really change how habitats work. So as an example, here's a paleo reconstruction of coastlines in North America. This dates to the KT boundary. And there's a few things I'd like you to notice. First, in the middle of the continent, we have the sort of remnants of the Western Interior Seaway that is now drying back. And along the Gulf Coast and Atlantic seaboard, we see a coast that's really quite different than what we see today. If we let a little time run by, we now see some change. So the Western Interior Seaway is essentially gone. There's a little bit of warm mesic habitat left in the Western US that's supporting that end Eocene community of turtles that are about to go extinct. And the Gulf Coast is starting to look more like the present day. For example, Florida's a thing, even if it's not connected to the contiguous continent. And then it's not really until 10 to 5 million years ago that these coastlines start shaping up in the form they are today. Okay? So that's sort of one thing. We have this big change in coastlines between the Eocene and now. The second fact I'd like to point out to you is that if you spend a lot of time staring at range maps of turtles, and I'm sure many of us do, you'll notice a lot of them seem to hug coastlines. So this is the range of the Florida softshell. It's essentially restricted to areas that were not emergent before the Eocene. They were underwater. Here's Pyxis from southern Madagascar, tightly hugging the coast, Batagur from Southeast Asia, even whole clades. These are the map turtles, very near and dear to my heart. And these are essentially a series of river endemics across the Gulf of Mexico. So we see this pattern of changing coastlines and many turtle ranges being centered in areas that were marine habitats 35 million years ago. And that sort of raises this question: might these global changes in sea level help explain the modern diversity of turtles? Okay, so that's sort of a new hypothesis. And to test it, we did something relatively simple. So we took our tree and then we went through all species of turtles and classified their ranges as being coastal. That's the left column here in green. So these are ranges that are almost entirely on coastal plains in areas that would have been underwater. Inland in the right column, so these are things that would have been emergent at that time, or widespread, so they're both coastal and inland together. So once with this data and our tree in hand, we can now fit a new type of diversification rate model. And this is just sort of a graphical picture of how this model works. So what we're doing is allowing turtles that live in different areas, coastal versus inland, to have different rates of diversification. Okay, so if you look at the green circle here, in coastal areas, we can speciate at some rate, S0, and that adds species to the coastal pool. These species can also go extinct at some rate, X0, that takes species away. The same for inland, and if you're widespread, you can also speciate and go extinct. Finally, you can disperse between these ranges, so ranges can evolve across the course of the tree. Okay? Now, this is the simplest version of the model. I'm not going to get into the statistical details of this, it's just too much for a short talk. But again, there's many possible models here, and we explored a large set of them and averaged across that uncertainty in proportion to how well they fit the data. So this is what those results look like. In the left box here, I'm showing you the net diversification rate for the 3 different areas. And sure enough, we see roughly 3-fold faster rates of speciation on coastal margins than we'd see in inland areas, whereas widespread is sort of intermediate. This change really seems to be driven by a change in the speciation rate. That's the right box. It seems that the overall diversification rate is higher because species are speciating more quickly in those areas. We can also use these models to reconstruct the history of shifts between these different habitats. So that's what I'm showing you here in the tree. The green tips are the coastal species. And one thing that really strikes me about this is essentially all of these transitions into coastal habitats post-date the Eocene-Oligocene transition. And that's demarked in the dotted line here. Now, the model has no real knowledge about timing of these events. There's no necessary reason it should reconstruct it this way. So the fact that it does it is suggestive to us. It's concordant with the hypothesis again. So taken together, we'd say based on these analyses, it does appear to be that modern turtle diversity seems like it may have been driven by rapid diversification on newly exposed continental margins. And it's really decreasing sea levels that explain both these patterns between the fossil record, where we have disappearances, as well as bursts of diversification in the extant species that we see overall in the tree. Okay, so I will leave it there with a few more acknowledgments to lab assistants over the years. Again, many museums and collections and individual contributors, many members of TSA, thank you, as well as computation and funders. And if I have some time, I will take questions.